Hi guys, I'm going to go through final exam for Thermo Kk 23-24 Sem 2. Let's just get through it. The first question says they want to estimate the molar volume for and molar volume and Z for carbon dioxide at T equals 310K and P equals to 8 bar. So as usual, this question, what I will usually do, like before from the first video from test 1, I would see what kind of equation they want. So first they want Rayleigh-Kwong EOS. So from before we have this formula. You know what? Yeah, we have this formula here. This is commonly used for the EOS cubic equation of for EOS, not cubic, sorry. Just for EOS in general, we use this. And for the value of Q and beta, you can determine from here and here. So this is pretty much straightforward, just plugging in formulas. Let's see my working here. Yeah, you can see here I use this equations right over here. Where is it? Yeah, I use this equation here. For beta, you have this omega, reduced pressure over reduced temperature. This one is just PR is P over PC, PR is T over TC. Sigma, you can that's omega. Omega you can find from here. This table here for they want RK, Rayleigh-Kwong, so it's here. And then for Q is phi alpha over omega TR. For phi is this one. Alpha TR from Rayleigh-Kwong is TR power of -1 over 2. And also it just I think I can skip this because it's pretty much very straightforward. But yeah, and then you have to do iteration, because from here you need to assume Z starting value as 1, and you have to do iteration until you get a constant value. Here I get 0.9642, and then I sub into the ideal gas equation. PV equals ZRT. Z you obtain from here, and then V is just algebra. But for Lee Kessler is the Z equals to Z naught plus WZ1. Z0 and Z1 you can find from the Lee Kessler correlation table. I think it's table C something, I'm not sure. Let me check. Pretty sure it's table no. It's table D. Yeah, appendix D. Table D1 up to D2, up to D4 actually, depending on your PR and TR value. And then just substitute the Lee Kessler equation, this one, and then you find the Z, and then you can find the V. Yeah, pretty much that's it. And second question says, what do they want? Determine the heat of formation of urea if the heat combustion of urea. Okay, here, okay, it is a lot, but it's pretty much very simple. So here they said they want the heat of formation of urea, so they want HF for this reaction. And then the value that they give is heat of combustion of urea. They give HC of urea is -63100 J per mole. So what is the heat of formation? So let's go through my answer. Yeah. So heat of combustion. Let's see. Oh, sorry, my bad. They want, let's just go through this question again. Sorry for the confusion. So they want NH2 plus CO. I don't really know the exact formation equation for urea, but let's say this is it. I won't balance it. So they want the heat of formation of this, but the thing is we don't know because it's not in the table, right? Heat of formation. Yeah, there's no urea in here. So what do we do is that, but they give the heat of combustion for this. Hc is negative 631,000 J per mole. So what can we, so we can find heat of combustion is, technically in general, heat of formation or heat of combustion or heat of what else, what reaction else is that, I don't know, any reaction you can, the general formula is heat of product minus heat of reactant. So this is it. And then they already give heat of combustion for this whole equation. They already give the heat of combustion. So negative 631,000 equals to the heat formation of product. My bad. Heat of formation of reactant. And heat formation of product you can find from this table. CO2 is in the table, H2O is in the table, N2 is not in the table because N2 is a mono element. You can't form a mono element, say N2 or O2 or H2, the heat of formation will be 0. So 1.5 O2 0. So you find from the table, let's see my working. Yeah, for CO2 you have this and this and this. Okay, the tricky part is that when you want to use heat of formation equation, it's actually NHFP minus NHF reactant, where N here stands for stoichiometric coefficient, where if you have 2H2O, then this will be multiplied by 2. Yeah. And if you have, say, you have 3 CO2 here, then this one will be multiplied by 3. But since it's 1 here, you don't have to multiply it. Technically, you have to multiply by 1, but it's very trivial. You don't have to really show it. So you'll get that. Next. Question 2. In the process, propane gas changes from initial condition of 5 bar and 105 degrees Celsius to a final condition of 25 and 190. So, remember when I said about residual property? This residual property, where residual property actually take account of real properties, where HR is equals to H minus HIG. Yeah, this is that question. So what do you want to do when you find this question? It's the same as finding heat of reaction technically, but then there is no reaction, it's just changing of temperature, changing of state. So they say here met at prop, so C3H, what is it, what is propane again? C3H8, yeah, C3H8. If they didn't specify what state it is, you can assume it as starting state is real gas, and you have P25, T equals to 190, and then you have to change it into ideal, which is C3H8 ideal. You are not changing any temperature or pressure yet, it's just changing of state. And then only then you can change the temperature. Because remember when I say when you want to use the heat capacity table, you have to assume it as ideal gas state. You can only use this table when it is ideal, so that is why when you want to change the temperature, you have to make sure the state is in ideal. So C3H8 ideal, P equals to 25, T equals to 190. Oh my bad, this is actually, the starting is P equals to 5, T equals to 105. P equals to 5, T equals to 105. And then you change it to real gas bag, which is P equals 25, T equals to 190. And then this is your enthalpy. This will be your negative HR. Wait, what did they want? Oh, they only want enthalpy. So HR, usually there will be SR here, but since they don't really want entropy, you don't have to find it. And then HIG, and then HR. So your enthalpy would be negative HR plus HIG plus HR. 1, 2, 1, 2. So HR, and then we will see the second virial coefficient generalized correlation. Oh my god, wait. Let me see. Finals, no. Slides. No finals. For residual property. This residual, no, this is fugacity. Yeah, okay. So they want second virial generalized coefficient. Second virial would be this one here. This long as formula. So let's go through my answer here because I have the complete table. Yeah, like before, don't waste time finding SR because they don't really want SR, but I'm just going to show you the calculation where if they ask for entropy. So the first part is when you want to find the HR reduced enthalpy. For the first state, notice how they have reduced pressure and reduced temperature. So make sure you label, you tabulate the data as initial and final state, because both initial and final have different reduced temperature and pressure. So be mindful of that. Don't forget about it. So first is calculation of they want HR, right? For the first part is changing real to ideal, so you want real enthalpy. So the formula for real enthalpy is this long formula, where dB naught over dTr is this blah blah blah. This is just method of plugging in formula, so it's not that difficult. Just make sure you bookmark this in your textbooks. Yeah, and then HIG is just using A plus BT plus CT squared plus DT negative 2 DT. R D naught D final. This is your CPIG, your basically your HIG. Yeah. Yeah, pretty much simple. And then for the second reduced enthalpy, second residual enthalpy is the same step as before. Like from this one, you have to find dB naught over dTr, dB1 over dTr, and B naught and B1, and then just plug inside the formula and you'll get that. And you'll get this. Make sure to not forget the negative, because when you're changing from real to ideal, it's the other way around, so it's negative. Okay. So question 3, did I go through? Yeah. So question 3, the feed stream to a reactor contains carbon monoxide and steam at 130 degrees. Calculate fugacity for each species in the stream. Estimate the percent of error. Okay. So they said in a feed stream to a reactor, so in a single stream, there's 0.6 mole of CO and 0.4 mole of water. The steam is water, right? And P is 130 and P is 180 m or 1 bar. And it goes to reactor and whatever, because the output doesn't matter because they only want in the input stream, in the feed stream. So they want fugacity for each species here. So they want F1 and F2. What is it? So for fugacity, it's really simple. Don't complicate it. So it's 12 March, right? So you're gonna use this formula, this generalized coefficient. Yeah, so it's quite I kind of skipped some working here, because or not the working is gonna take a whole page, but I advise you to not skip any step. I only do this because I've already done this question a lot of times, so I trust myself enough to not do any mistakes. But if there's any mistakes, please point it out. Anyway, in exam, please don't skip the working. So what I do is I'll tabulate my every data I have. So so you have this, you can find from appendix B for carbon monoxide. Carbon monoxide, you have 0. Just basically take out every information here, 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 and here, and list and tabulate them. And you also find the reduced temperature and pressure, and then this one. So for the thing is, for fugacity, it's, if there's only one species, the working will be quite direct. But since this is a binary system, meaning there's two species at once in one stream, so you have to find the combined properties. They are called properties, right? Yeah, you have to find the combined characteristic properties of these two species. So IJ, I don't know if I've said this before, but I meaning species I, J meaning species J. So in this case, CO is I, H2O is J, or I can be as 1 or J can be as 2. It doesn't matter, it's just the way you refer to them. So if it's 1 1, then it's just carbon monoxide. If it's 2 2 or JJ, then it's H2O. So if it's 1 2, then it's the combined property of both CO and H2O. And if you want, then there's a specific formula for each property if you want to find the combined properties. So like here, for Wij is just Wij is Wi plus Wj over 2. Tcij is Tci times Tcj power of 1 over 2. You can, if the question didn't specify, you can safely assume Kij as 0. Really important. And Z combined value of Z times R times Tcij combined temperature over Vcij, the molar volume. So the thing is, okay, here you have to pay attention in the unit, because here it's cm cube per mole, and here is bar and here is K. So look at the R, you cannot use 8.314 because it's J mole K1. So you have to use 83.14 because you have cm cube, bar, mole, and K. So use 83.14 for your R value. And then what else? Vcij is Vc 1 over 3 plus Vcj 1 over 3 over 2 power of 3. And Zcij is Zci plus Zcj over 2. Yeah, make sure to show your working if you don't trust yourself enough to not make any mistake. Please show your working and tabulate them. And the second table is find the combined reduced temperature and B naught, where B naught, the formula of B naught is 0.083 minus 0.422 over TR 1.6. B1 is 0.139, 0.172 over TR 4.2. Yeah, and then you find the combine. You can't find combined BO, so you just sub in this TR instead when you want to find B0 12 and B1 12. But Bij, there's a formula here where Bij is RTCij. This Bij for B11, so it's RTC11 PC11 times B01 plus W11 B11. It's pretty lengthy, but it's easy. It's very direct calculation, so you just have to familiarize yourself with the formula. And then the next step, after you have find all these values, find the delta 1 2, and then you can find the Fogarty coefficient from this. You can find first find the delta 1 2, and then find the Fogarty coefficient, where delta 1 2 is this one right here, and then find the Fogarty coefficient from these two equations here. And once you find the Fogarty coefficient for first species 1.011 and Fogarty coefficient for the second species 0.993, and then sub inside this equation here, YIP, where YI refers to the mole ratio obviously, and pressure is referring to the system's pressure. And then you can find the Fogarty for each species. So the next question demands you to find the percent of error if you repeat the calculation in A, based on the assumption that the mixture is an ideal solution. So if you want to assume the mixture is an ideal solution, then your assumption would be ideal mixture is equals to ideal solution. This is your assumption. So yeah. And then there's a specific formula, which is this one here. This is you use the second term virial coefficient for this kind of question. And then the percentage of error is just this one minus, so basically your ideal solution, Fogarty for ideal solution, minus Fogarty of mixture over Fogarty of mixture from this one. This is Fogarty for the mixture. Yeah, very straightforward. So question 4, for the binary system acetone 1 and water 2, the Wilson equation constants are V1 blah blah blah. Write the equation for GERT. Oh, okay, this is a lot. Again, okay, I don't really know how to simplify this any further, because this is just formula. I don't know how else to say it, but yeah, the Wilson equation, because they want Wilson, right? Yeah, based on the Wilson model. So they want you to express the function of liquid phase mole fraction and x2 based on the Wilson model. So they didn't give any x1, or they didn't give any value for x1 and x2. So in your Wilson equation, you can just write your x1 and x2 as x1 and x2, because you don't know what is the value. So this is your Wilson equation here. So you know the value of A12, because A12, the formula is this one here. A12 equals to V2 V1 exponential function of A12 over RT, where R is 8.314 and T is 363. Again, make sure to cancel out values. Make sure to use the right gas constant. Yeah, and then just express it as Wilson model or Wilson equation. Okay, you just leave your answer like this. And then the second question, they said, what did they say? Oh my god. Assuming the validity of modified Raoult's law. So modified Raoult's law will be for liquid mole phase. So your modified Raoult's law will be this one. P is equals to actually P is equals to xi gamma y pi z. So this modifier is, if it's valid, then you can use this equation. Then they want the pressure and vapor phase mole fraction, given that the liquid phase mole fraction is x1 0.25, so your x2 will be 0.75. what the hell, right? So from before, this is just yeah, because before this they said to use the Wilson equation, based on Wilson equation. So the second part, you also have to use Wilson equation, not Margules, unless they specifically state Margules. So if the question before states Wilson, then you have to continue using Wilson equation. So for Wilson equation, you need to find, so for, if modified Raoult's law is valid, your equation will be xi activity coefficient or gamma I pi set, right? So pi set you can just easily find from Anton equation, which is ln p set equals to a plus b over t plus c, right? So pi set is settled, xi is settled because they gave the value. So you need to find the gamma value. But for pressure, since have they given the value of pressure? No, not yet. So what is left is this value and this value right here. So one by one, you can find gamma first. So from gamma, you can find from this equation right here, because you have value of x1 and x2, you also have value of a12, and so you can find your gamma 1. So like I did over here, you can find gamma 1 and then gamma 2. So after you have already found your gamma 1 and gamma 2, you can then find your combined pressure. So this one. So an extension of modified Raoult's law, if you want to combine, actually Raoult's law, not modified, if normal Raoult's law will be YIP pressure equals to XI FI fugacity, right? But in bubble point calculation, or actually in normal calculation, your Fi will be Pi set. So actually you can just rewrite this as Yi times total pressure is equals to Xi times vapor pressure. This is your Raoult's law. But if it's modified, then it will be there's an additional of gamma. So what would it be? It's actually just addition of gamma actually. So it's xy like before. So you have already found pressure, combined pressure. You already know, because in the question they already give you the x12. Gamma you already found from before. Pi set is also found from before. So yi is equals to xi gamma I pi set pressure. So that's it. And then you can find your y1 and y2. So next, what do they want? If the system above at composition of Z1 0.45, Z2 0.55, assuming that Raoult's law is appropriate in these conditions, prove that at this pressure the system lies in two-phase region. Okay. So if you want to prove that the system lies in two-phase region, your criteria would be pressure, dew point pressure must be less than the pressure of the system, less than bubble pressure. This is your criteria. So you have your pressure, right? You have your system's pressure, which is what is it? 222.96. Wait, no. Which is 120 kPa. Sorry, my bad. Which is 120 kPa. So what is left is to find the dew pressure and bubble pressure. So in in bubble point or bubble pressure, you have to assume that when in a system, so what is actually bubble pressure is you want to calculate the pressure when the first bubble appears. So before the first bubble appear, that means the whole system is everything is liquid, right? So L equals to 1, and your assumption will be Zi is equals to Xi, because every species in that system is all liquid. So every mole fraction is just Xi, because Xi represents mole fraction of liquid, where Yi represents mole fraction for vapor. So since there is no vapor, so your the mole fraction that they give here all represent Xi. So that is your assumption, Zi equals to Xi. And we also know that from Raoult's law, P is equals to Xi Pi Z. So X, since we assume Xzi as Xi, so just find the summation, which is 0.45 times the vapor pressure for first species and this one. And you get bubble point pressure. For P due calculation or due pressure calculation is the opposite of bubble point. For bubble pressure, so we are going to assume that every mixture in this system are all vapor. So when everything is vapor, then Zi equals to Yi. Since Xi is 0, so Xi doesn't represent anything. And the formula for due pressure is 1 over Yi over Pi set, or summation of Yi over Pi set. Yeah. And then you check whether the system's pressure, 120 kPa, lies between these two values. And if it lies between these two values, then the system is in two-phase region. Congrats, you just finished 4 out of 5 questions. Let's see the final question. The ethyl benzene production by reaction of styrene, ethyl benzene, styrene. Okay. This is chemical reaction equilibria. Okay. So let's go through my working. Okay. Again, this chapter is a lot, but I really need you guys to listen carefully on which formula that you guys have to use, because it can be quite a lot. Yeah. And then how do I explain this? Okay, let's go through one by one. Okay, so the general formula for effect of temperature on the equilibrium constant, or G over RT. Let's see, what's the question again? So they say the reaction reaches equilibrium at 500 degrees Celsius and 2 bars. They want you to find the composition of the system at equilibrium, and the reaction consists of 2 mole of hydrogen for each mole of styrene. So your initial would be, this is your initial condition. There's 2 moles of hydrogen for each 1 mole of styrene. Okay, so for styrene, okay, so this one here, right here, this is the general equation that you have to know, because this here you have to find actually, to condense it, is actually you have to first step you have to find the G naught over RT from the long S equation. Second step is you want to find the equilibrium constant, which is K, from this equation, and then find K. Third step is find the mole ratio, right? So the summation of Yi is equals to P over P naught power of negative V times K, where V, what is V? What is V? V is just the stoichiometric coefficient. Yeah, V is actually just stoichiometric coefficient. Yeah, and K is from here. So if you already find K and you already find and you already know the pressure of the system and the initial pressure, then yeah, it's pretty much very simple. So these are just the general steps to solve this question. So let's solve one by one. So what is G naught? G naught is actually just the Gibbs free energy. So we already know from the table. You can find the Gibbs free energy for this one, and styrene, there is the value in the table. H2, there's no value for H2 because it's a mono element. And heat of formation, this is actually heat of formation, find from table. So this is complete, it's already solved. You can find this, where R is 8.314 and T naught is 298, because we are using that table, right? We are using this table right here. So we are going to assume the starting temperature as 298 K. Yeah, so that's done. The first part is done, and then you have to find the HO over RT, where HO is actually here. This is HF, this is G, Gibbs free energy, this is also heat of formation. From before you already find, and then over RT easy. 1 over T. T is, what is the, they said it reaches equilibrium at 500 degrees Celsius, so this is 773. Yeah, 773 K. So 1 over T. T here is not T naught. T is the temperature of equilibrium, so it's 773 K. Yeah, and then you have to find the Cp naught over R. The Cp naught over R is, I think you guys are familiar with this equation. This is technically your CPIG, your heat capacity, your to find the enthalpy for ideal gas. Remember, so you have to find your ABC. Okay. Also remember, for ABC you have to pay attention to the number of moles. So yeah. And also for ABCD, for A is actually I'm pretty sure it's product minus reactant. Yeah, and same goes for B, C, and D. And then yeah, find that. And then you guys are also familiar with this Cp naught over R dt. This is actually your SIG, your entropy, ideal entropy. So nothing new. These are all actually, if you look closely with the equations, it's actually nothing new. It's just applications of formulas from before, and they use it back again. It's just that how they use it is different. But if you look closely, it's just the equations you have used before from chapters previously. And then you already found your G naught over RT, which is negative 3.52. And then sub inside this equation, the ln K equals to negative G naught over RT, and you get your value of K. And then from before, okay, this is the tricky part. Formula for Yi, or the mole ratio, it's actually Ni naught plus Vi reaction coordinate over N naught plus stoichiometric coefficient times the reaction coordinate. So what I want you to do is construct this table. So first, the Vi, or stoichiometric coefficient, is 111, right? So it's actually product minus reactant. To get the sum, it's just product minus reactant, so 1 minus 1 minus 1, so you get negative 1. And NIO, or the initial state, is, yeah, there's a difference between NIO and N naught, Ni naught and N naught, where Ni is actually your initial mole. Yeah, initial mole. So styrene, there's 1, because there's 2 moles of hydrogen per 1 mole of styrene. So there's 2 moles of initial starting point, there's 2 moles of hydrogen, and there's 1 mole of styrene, but there is no ethyl benzene in the starting reaction, right? So it's null. And then to find the N naught is just you plus everything together. So that's the difference between N naught and N initial naught. And then just plug inside this equation, you will get this. Your equation, your expression of yi in terms of reaction coordinate. And then you plug inside this where yi is y product over y reactant R1 y R2 equals to P over P naught negative V times K. Yeah. Okay. So yeah. Okay, yeah. And then by quadratic equation, you will get two values, which is 2.028, and the first reaction coordinate is 2.028 and second is 0.9716. The criteria to choose which reaction coordinate is this cannot be more than 1. So since this is more than 1, it's rejected and you choose this. And then for B, they said, what if with 2 bar, 2 bars, okay. One more thing that I forgot to say is that the starting, the initial condition, you assume it as 1 bar and T of ideal 278K. Sorry, 298K, my bad. So this is why 2 over 1, because the equilibrium pressure is 2 and the starting pressure is 1 bar. So that is why P naught equals to 1 and P of the equilibrium is 2. And then the second question say, what if it increases up to 5 bar? So you repeat this step, you're going to repeat this whole step, but instead of 2, you're going to replace it by 5. And just like before, quadratic equation, if it's more than 1, reject it, except if it's lower than 1. And then after you find the coordinate value, reaction coordinate, this value, you sub inside these 3 equations here to find the mole ratio or the composition for each species. And you're done. If I'm not clear enough, just tell me. Maybe I can explain to you privately. But that's it for Thermo Kk. See you guys. Bye bye.